We had great fun doing these case studies. I think you will see that all of them are solved in exactly one rule. Now, Groove is a tool in principle for state space exploration, not for model transformation, so it differs from many of the other tools here. So here you see, for instance, the rule that creates one node that says hello world. Here's a rule that creates a larger structure. We interpreted this as having to also put some sort of text out. Now that is not native functionality, but we extended the tool for this purpose by adding to each rule something that it should print on the standard output when it gets applied, which is in the printf format of Java. So it has this rule has two output parameters, and this is the message that will then be put on the standard output. And here you see the actual values of the parameters. So if you apply this rule, and since this is running from Eclipse, then you will see hello participants on the standard outputs. So that's all I wanted to say about this, because I think the other rules are more interesting, especially the counting rules, because here we can show off the capabilities of Groove for amalgamated rules. Now we saw some of this in the Henshin solution, but here you can see a little bit more. For instance, this is the rule that counts 3 cycles. What you see here, you see 3 nodes. It is specified what the structure between those nodes is supposed to be by regular expression paths. So of course there are edge nodes in between, but this says there should be an inverse source edge from an edge node to this node, followed by a target edge from that edge node to this node. And that connects these 3 nodes in the required cyclic structure. This specifies that the nodes are actually not the same, because natively Groove always matches non-injectively. And then this node says that you want to find this pattern everywhere. And this thing says that you then want to count the number of matches that you found. So I think this is the only solution that actually really uses one rule and doesn't have to specify the explicit counting of the number of occurrences afterwards. So this is also printed on the standard output, but just to make it visible in the graph, I added a node that then shows the number of matches that were found. So let me see, why is this not working as it should? Why is this not working as it should? Did it crash on me? Okay. As you see, we're working on this tool all the time, and sometimes it's not quite stable. Let's go back here. So now it produces the required report, which for this graph reports 3 cycles. So I don't know if I can find them straight away, but the idea is that you should do this in one go. And that goes for all the counting rules. So I'll go back to the initial state now. So this builds up underwater the state space of all the graphs that it has found, but this has no purpose at all in the case study of this kind of system. So I go back to the initial state and try the other rules. For instance, try counting the dangling edges. Again, I mean, you specify the structure that you're trying to find. You say you want to find all the instances of it, and then you say, this is the number of instances that I find I want to do something with. You could do lots of other things. You can constrain the number of instances, for instance, rather than report them. So that's the counting rules. Then there are rules that change the structure. I mean, typically quite easy as for the other tools, because it's native functionality essentially. This one deletes nodes and incoming and outgoing edges. This one just deletes a node without deleting the incoming and outgoing edges. Here you see again universal quantification to make sure that you delete all the incoming and outgoing edges. The migration rules, this tells you to change all the edges that are part of a graph. Here you see actually several occurrences. So again, this rule will do the trick for everything in the graph in one go. You can match it. I'll show you the state. Matches everywhere, and then it transforms this graph. You hardly see what's happening, because I think the colors are they show rather well. So previously it was nodes, edges going here, and now it's GCS going here, and some other things have changed. But I think you all know the actual exercise. Transitive closure, similarly, just one rule which applies everywhere. You look if there's not already an edge there, in order to make sure that you only create edges in the case that here you again see such a path expression that makes sure that you only match those paths that go through at least one other node. This is a perfect time because I'm done.
Okay.
There were several remarks. One regarded control was a very cute remark, because normally this works like you can apply every rule all the time, and if I go back now to this other grammar, that would mean that you can apply a rule like this all the time. If you let roof run, it will actually, natively at least, create an unbounded number of these greetings. But there's a control language by which you can then impose ordering or constraints on the execution. So I added this because it was requested in one of the remarks. Now it says either you do this first rule that creates one greeting, or you do this other rule, and then, well, there's a rule that I didn't show, which actually concatenates strings. So that was one thing, I think, and there was another thing. There were some misunderstandings which I prepared. It was not so interesting, I think.
Okay, then if there are no questions, then
I have a question. What does your solution do for this structure on the platform? If you want to insert transitive edges, would you insert multiple or only one?
You would insert only one, but let me think, because it actually tests for the existence of the structure, but it doesn't distinguish matches that only differ by the intermediate edge. Actually, the intermediate edge is not even in the rule. You just look for paths, and whenever you find two nodes that are connected by such a path, that's one match. But you wouldn't find multiple matches, so it only inserts one edge. You could have put the edge in there, and then it would have, I'm not sure, you can actually make a choice whether that edge should then make a difference to the match, and therefore should generate two edges.
Right?
You can use existential. I mean, there's lots of ways you can fine-tune this, but as given here, it only creates one edge for every two consecutive edges in the original path. You look as if that didn't answer your question, but
maybe we will I was not sure when I was reading your solution.
Well, you can say that the exercise is not unambiguous, but whatever the exercise was, we can certainly, with minimal change to this rule, find a solution.
We already say it's false correct, so yeah, not important.
Okay, and yes,
it's complete.
so thanks very much, Arne. So